Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 3.1, Factor Notations. So, factors. Factors are very useful in a lot of ways. Back when we're doing complex numbers, I've talked about how you can see complex values as factors, and there are also a lot, especially during next chapter. With matrices, we can do a lot of crazy things with factors. So, a factor is defined as a quantity with a direction and a magnitude. So, there are two main types. One of them is called the position factor, and the other is called a direction factor. What they mean is essentially position factor defines a certain position from the origin. So if I have a 2D vector field of x and y, then say a factor pointing from the origin up this way onto a location defined by 1 and 1, will have a factor quantity, either a column or a horizontal row. A factor can be either a column or a row, and basically they mean the same thing, and you use different version of them in different purposes that aren't really strictly true or false when it comes to factors. So when you go do a horizontal factor, you have two values with a comma in the middle separating them. So a general row factor, you get a x and a y, and that would be your R factor. And also factors are denoted by a line underneath or a bold type. So if it's a printout, then it would be bold. If it's a single underline, it is a factor. Handwritten anyway. So this is the position factor, and direction factor. If I define the same plane, and I'm gonna use 1, 1 again, this time 1, 1 can be anywhere. So if I have a direction 1, 1, then it can be a direction factor over here, it can be a direction factor over here, it can be over here if I wish. Doesn't need to start on the origin. So direction factor is essentially an unconstrained position factor, whereas a position factor always start on the origin. If you take away this initial location, then it turns into a direction factor. So this said, we have two other things for you to consider. One of them is called a scalar value, and one of them is called a factor value. So I've defined at the start that a factor is a quantity with a magnitude and a direction. A good example would be velocity. So velocity, you can go very fast or very slow, go forward, backwards, left, right, north, east, southwest, and any combination of the above. And whereas scalar, it's more like, say, temperature. It doesn't have a direction, and it can be not non-uniform. There can be a scalar temperature gradient across a space, and you can kind of describe that using factor fields, but I'm not gonna go there anywhere. because it's just way too much for A-level purposes. What you need to know is that if a scalar quantity have a direction, it will be a vector quantity. I missed a y there. Velocity is speed time with a add-on direction. So you can go a very high speed, but that doesn't tell you where you're going. But if you describe it with a velocity, then you do know the direction. With that said, now we need to talk about the magnitude and the modulus of a vector. The magnitude of a vector is, as we have talked about in the complex section, basically you apply trigonometry to find the length of that line. It works 2D, it works 3D. So say if I have a 3D vector R is equal to arbitrary x, y, and z, then we can define this, the magnitude of R, which is denoted by modulus symbol, squared is equal to x squared plus y squared plus z squared. This is the definition of the magnitude of a vector, where the xyz can be a n-dimension vector value, so you can add more if there are more dimensions, but as far as I know, you're only ever going to do 3D during A level, so that would be fine. Now we have to, with us talking about magnitude, we have to also talk about the normalized unit vector. So a unit vector is called is defined as any vector that has unit length of 1. So a unit vector on the x direction would be a 1, 0, 0 vector. This would be x direction. You can also write a vector with an arrow on top. So for the direction x, the unit vector is 1, 0, 0. For another vector x that is not a unit vector, actually I should denote this as x hat. A hat means unit vector, and just arbitrary x can be just x 0, 0 with any value of x. I'm pretty sure there are complex fields, but for the purpose of if you're not going to be a university mathematician, then I'm pretty sure you do not need to know a complex field, as of you can put any value, but we'll stick with real numbers. With that said, if you want a y unit vector is 0, 1, 0. If you want a z unit vector, you get 0, 0, 1. What about some other arbitrary direction vector that I want to get a normal value of? Say I have 2, 3, and 1 as my unit as my vector n. You'll see why I use n in the future, but for now I'm gonna stick with n. To find the unit n hat vector, you will want to divide that by the modulus. So n hat is defined as n on mod n, and mod n, that's h, mod n is equal to the square root of 4 plus 9 plus 1, which is root 14. And so n hat is essentially 2 on root 14, 3 on root 14, and 1 on root 14. This works for any factor n, x, y, z, and you can use this on any factor to find the normal, and the normalized unit factor rather is essential for finding distances, for finding volume and all sorts of stuff. So when you only want a direction, go with the unit factors. Now, I have talked about a factor having 3 components on a 3D space, but what you are more confident with dealing with is just the Cartesian kind of coordinate system, and turns out that you can do the same. So for Cartesian x, it's the first element of the factor, Cartesian y is second element of the factor, and Cartesian z is the third. And you can always translate from the factor into just plain coordinate form. For direction factors, it's a bit more difficult to do in Cartesians, but for the purpose of a position factor, say r in this case, then the position or the dot that is described by the position factor has x coordinate x, y coordinate y, and z coordinate z. And that's just a definition thing that you need to know. And finally, after all these mess of us of all these new stuff that you need to know, it's time to talk about parallel and equal factors. So these are all line factors that I've described. How do I know if they are the same factor, especially when it comes to directional factors? For directional factors, you don't need to be on the same dot to start and end. However, they all have the same magnitude and they all have the same direction. So for all factors, factor r, you can kind of say that it is a this is any arbitrary r factor. You can always say that it is a factor a at a direction or a distance along a direction d. So this will be a line, and A is a starting point on the space, just one particular dot on this line, and a distance away from this dot along this direction. It's almost too difficult to visualize. I will try to do it on a 2D surface. Say I have a point 1, 1, so this is the A, and I have a direction of 0, 1, 0, which is a direction vector pointing upwards. And if I want to go from 1, 1 to 1, minus 1, this length is down 2, and therefore lambda is minus 2. You can see this in a 3D space, and it would work on 3 coordinates. For the purpose of this introductory video, I'm not going to talk about that because it gets very complicated very fast. However, I think it's important to note that if for a certain R you have a different A, you have a different lambda, but you have the same D, then you will get a parallel line. If you get A as the same and lambda is the same, then you will have an equal vector. If you have lambda the same, D the same, and A difference, then you have an equal vector displaced along its length. So rather than having a line and a line here, you have a line on top of your own line, except like on a different kind of overlapping location, or even not overlapping at all. It might be a few 100 miles apart, but it doesn't really matter. It doesn't apply in a lot of circumstances, as long as you know that if you have the same direction vector, then in almost all cases you get parallel lines. For perpendicular lines, that's a different story, and we have another method to calculate that, and that would have to wait for the next one, where we talk about scalar and vector products. For now, I'm gonna end this video here because it's been quite long. There isn't really enough stuff here for you to do any kind of questions, and yeah, if you have anything that you want to ask about vectors, to let me know in the comment section below. But for now, this will be the end of this video, and I will see you on my next one.